Hello all, we shall look into the next module, which is angle modulation. Okay, in this angle modulation, as was discussed earlier in the previous module, when we were talking about the basics, in angle modulation two different types are there. One is a frequency modulation, other one is phase modulation. Both of them look actually alike because they all belong to the angle part of a carrier. So it's the angle which is getting changed every time when you perform this kind of modulation, but there is a slight difference. So they're almost identical with a slight difference in between them. Okay, so we shall try to understand it. So what is basically the definition of these are all the things that we'll be talking about in angle modulation. Basic definition: frequency modulation. We'll be talking about narrow band and wide band, FM transmission. Uh, then we'll talk about the bandwidth of FM signals, generation of FM, demodulation. We'll also talk about the stereo multiplexing. Then we'll talk about PLL, nonlinear effects in FM, super heterodyne receivers, and all those things. Okay. So coming to the definition of angle modulation, we have already seen the AM definition. S of t is equal to AC into 1 plus M of t cos of omega ct. This type of modulation basically changes the amplitude of the carrier. If you can observe, 1 plus M of t is present before cos omega ct, okay, which is the amplitude part. Now when you try to put the the variation in the angle of carrier, so obviously it comes within the cos, and you can see that in the next slide, the second slide, S of t, next equation right here. S of t is equal to AC cos of omega ct plus theta of t. So amplitude would remain constant, but the angle is getting modulated or changed. Such a kind of technique is what is called angle modulation. So this omega ct plus theta of t, which is in total the angle part, it can make even either the phase or the frequency to change. So this is about the angle modulation part. So how do you represent basically the angle modulated signal? So we have already discussed about this. Special cases for the phase modulation, the phase is directly proportional to the modulating signal, that is theta of t. And for frequency modulation, the phase is proportional to the integral of m of t, so that theta of t becomes equal to df integral minus infinity up till t m of sigma d sigma. Okay, where frequency deviation constant df has units of radians per volt second. So this deviation is very, very important. So what is the equation for instantaneous frequency? We can write it as omega I of t is equal to d psi of t divided by dt, where psi of t can be written as integral minus infinity till t omega I, which is nothing but the instantaneous angular frequency, and a function of some variable sigma, t sigma, where psi of t is omega ct plus theta of t. So phase modulation occurs when instantaneous phase is varied in proportion to that of the message signal. Okay, that's the difference. So how do you write a frequency modulation? Frequency modulation occurs when the instantaneous frequency is varied linearly with the message signal, as we know it already. Okay, so what will happen to omega I of t? Omega I of t is omega c plus df of m of t, where theta of t becomes equal to df integral minus infinity till t m of sigma d sigma. So the resulting FM will be S of t is equal to AC cos of omega ct plus df integral minus infinity till t m of sigma d sigma. So this becomes the equation. So how do you basically see the block diagram for a frequency and a phase modulator? So you have m of t, you integrate it, that is when you get integral, and then you will have mp of t, and then you basically use a phase modulator. So this integral m of t would come and sit at the phase part, which is theta of t. So if you can go back and observe, this equation, write this equation right here. If you observe this equation, theta of t is basically the phase part of it. Okay, so now this equation says that would suggest that in the theta of t part, which is a phase part, you basically see integral m of t coming and sitting. So that is why this kind of block is put here. So after integration, you put a phase modulator, it becomes a frequency modulation. So the vice versa is the phase modulator block. What is it? You see a differentiation being done, and then you put a frequency modulator. So once you have m of t with a differentiator, and then you put a frequency modulator, in theta of t part, you would already have an integration sign, and now you are differentiating m of t. So what you get is basically m of t itself. So you will have m of t sitting at theta of t part. So that becomes the phase modulation. So even though phase modulation is not there in the syllabus, we had a small discussion on that. So when you have a sinusoidal modulating signal, if a band pass signal is represented as some s of t equal to r of t cos psi of t, where psi of t is omega ct plus theta of t, then the instantaneous frequency of FM signal is given as fi of t, which is equal to fc plus 1 over 2 pi d theta of t divided by dt. Similarly, the frequency deviation, that is the amount of deviation which happens when the modulating signal is applied, you will have it as d of t, which is equal to f of t minus fc, which is equal to 1 over 2 pi integral, d by dt of theta of t. So the peak deviation will be delta f, which is maximum of 1 over 2 pi d theta of t divided by dt. And delta f is related to the peak modulating voltage, which can be written as delta f equals 1 over 2 pi df vp, where vp is the maximum value of m of t, which is the peak voltage. So peak to peak deviation will then become delta f, which is max of 1 over 2 pi d theta of t by dt minus minimum of 1 over 2 pi d theta of t divided by dt. Okay. What are the advantages and disadvantages of angle modulation? Constant advantages, constant amplitude means efficient nonlinear power amplifiers can be used, which is very advantageous. Superior signal to noise ratio can be achieved in comparison to that of FM if bandwidth is sufficiently high. Okay, these discussions, at least the second one, we'll have it in the module number 3 when we talk about the noise in the amplitude or noise and analog modulation techniques. Okay, there we'll try to derive the expression for signal to noise ratio at different points and see how it is superior to AM. Disadvantages usually requires more bandwidth than AM. It's more complicated hardware. Okay, this is a disadvantage of it. So we'll also try to now summarize the things that we discussed. The peak phase deviation is given by delta theta, which is maximum of theta. Delta theta is basically related to the peak modulating voltage by delta theta is equal to dp into vp, where vp is the maximum modulating signal voltage. Phase modulation index beta p is delta theta. Frequency modulation index is given by delta f divided by b, where delta f becomes the frequency deviation, b is the bandwidth. So normally we can write it as 2fm.